Okay, so let's start. So I'll have two classes for review. Today's class is basically on figuring out how to identify what concept to apply for a given problem. So in my opinion, what will make this exam particularly hard is that it covers multiple chapters, uh, 13, 14, and 15. And when you see a question, it will be something like this. You will not have the question number in front of you, so you don't know it's from chapter 13, 14, or 15. So how do you go about figuring out what concept to apply? Okay, so what I did was I created this sort of a sheet which I distributed, and that's how I go about figuring out what concept to apply for that particular problem. And it really covers all chapters 12 all the way to 15, and there's a similar sheet. Well, essentially the same sheet applies for the rest of the course, so the rest of the 4 chapters. Okay, so first of all, the easiest thing you can do is figuring out if the problem is a kinematics problem or not. And for a kinematics problem, you will see that the question will ask you velocities of one point given the velocity or acceleration from some other point, and you wouldn't get information about the mass, inertia, things like that. So in which case, you're sure it's a problem in kinematics. So number 1 on the sheet. Now this exam does not quite cover chapter 12. Okay, so you do not have to worry too much about this part, because you will not get a full-fledged question on this particular aspect, because only the last part, 12.9, I think 12.10 or 9 is covered in this exam, which is relative velocity. Okay, so once you rule that out, the next thing to look for in the problem is, are you asked to find velocity when the object moves a certain distance or vice versa? So in this case, you're asked to find either velocity as a function of distance or distance as a function of velocity. You'll be given velocities at a certain position, and then you'll be asked to find velocities at another position, or vice versa. You'd be given the displacement and asked to find the velocity, in which case this is a question from chapter 14. Okay, and chapter 14 was about principle of work energy and conservation of energy. Now, how do you choose which of the two concepts to apply? Well, if you see that the problem has only conservative forces, okay, and there are only 2 conservative forces we've talked about in this course, gravity and spring. Only those 2 forces, go for conservation of energy. Okay. However, if there are non-conservative forces, examples are external force, moment, friction, then use work energy. Okay. The next thing is, so let's say that you see the problem, it's not a velocity as a function of displacement, then ask yourself, are you asked to find a velocity as a function of time? So velocity as a function of time, or you're asked to find the time when you're given the velocity. In this case, it's a question from chapter 15, which is principle of impulse momentum. What you do is, if there are external forces and moments, then you apply the principle of impulse momentum. If there are no external forces, or forces are internal, so for example, if two spheres collide with each other, and if you look at the system as a whole, then there are no forces or impulses, in which case you can apply conservation of momentum. Okay, and the linear and angular depends on the circumstances. So if it's moving around an axis, then it's going to be angular momentum. If not, it's linear momentum. And then finally, if it doesn't fit 1, 2, and 3, that's when you go for 4, which is applying Newton's law, F equals ma. And then it can be a problem where you got to use coordinates xy, coordinates r theta or nt, and that's usually very obvious. If you're given, well, actually I have it here in my notes. If you're given the equation of, so this applies to 4, if you're given the equation of a curve in r equals theta coordinates, then clearly you have to use polar coordinates. If you're given the equation as y equals f of x, then use tangential normal coordinates, and if none of those two apply, then it's a Cartesian coordinate problem. Okay, there is an exception over here. This is an exception to the rule. That is, you might be asked to find velocity after a certain time, but if the force is given as a function of displacement, then you cannot do that. Okay? This is the only exception. Again, we will talk about this a little later. I'm not trying to, I will not ask you a question on this exception for this exam, so don't worry about it. But in the final exam, we'll go through this again, and I will actually talk about how to identify this and solve this problem. But for now, do not worry about the thing in blue, this thing. That's something to keep in mind. What else? Now, another thing which will make this particular exam hard is that sometimes it is a mixture of things. So, for example, it could be a problem where you have to first apply work energy and then projectile motion. So, example of that problem is here, and you must have seen such problems. So, here is an example where it's clear from looking at the figure that it involves two things. One is sliding from A to B, where you have to apply one principle, which is clearly it's not just kinematics, and from B to C it's projectile motion. So you got to be able to understand which two concepts from two different chapters to apply. So that is another aspect which will make this exam hard. So that said, here's something which you might want to note down. Our goal today is to basically take random problems from the book where we don't see the question number and solve it using this approach. Okay. Oh, I forgot to mail this, but the whole of these questions are actually on Blackboard. If you go to lectures and scroll all the way down, then it's already posted there. So you can download that. You don't have to copy this. And of course, I'll have my notes, but I posted there. I'll do the same thing for the next review. So if you came late, didn't get the sheet, I've put some over there on that chair and some over on that chair. Okay, let's start. So let's read the question and try to apply this. 2.5 megagram, which is really 2,500 kilogram van is traveling with the speed of 100 kilometers per hour when the brakes are applied and all four wheels lock. So when all four wheels lock, it's going to slide. If the speed decreases to 40 kilometers per hour in 5 seconds, determine the coefficient of kinetic friction between the tires and the road. Okay, so you're given the speed is 100. And the new speed is, so let's call this V1, this is V2 is 40 kilometers per hour. Initially the time is 0, finally the time is 5 seconds. Now in this question you are told to find the coefficient of friction. However, some of the information follows. You're given the velocity at different instances of time, right? So if you look at the sheet, 1 is ruled out. In fact, it's ruled out for this particular exam because I'm not going to ask you full-fledged kinematics problems. If you look at 2, is velocity given as a function of distance? and that's incorrect. In this case, it's number 3, where you're told velocity has different instance of time. So this is 3 from okay. So it's 3, which means we can either use principle of impulse momentum, or we can use conservation of linear. In this case, it's clearly not moving in circles or about an axis, so it's linear momentum. In this case, since there are external forces, which are basically friction, it is not a problem involving, it's not 3b, but it's 3a, which is external forces and moment. So it's really 3b from the sheet. Okay, so when you have a problem and you can draw a free body diagram, if you're even not, sometimes we ask you to draw a free body diagram and that's part of your credit. But if you're not asked to draw a free body diagram, and if you can draw a free body diagram, like for a kinematics, you shouldn't draw one because there's no F equals ma involved. In this case, if you draw a free body diagram, you'll actually get more points, and that is if you have not asked it. Okay, so free body diagram, assuming it's going to the left, N is upwards, mg is downwards, and the friction force is to the right. So for a particle, it's okay to draw whatever the object is as a particle or a block, because we don't care about its dimensions of the object. So this is the free body diagram. Try to draw a free body diagram if it's a dynamics problem, please. Okay. Even if you're not asked. So, as I said, this is principle of linear impulse momentum. Okay, which states that mass times v1 plus integral f external dt equals mv2. Okay, so the mass is 2500 kilograms. The velocity is given in kilometers per hour. Let's convert that to meters per second. So 100 times 1 kilometer is 1000 meters, and 1 hour is 3600 seconds, plus F external. So F external is the friction force, which is mu kmg. So mu kmg, and since that force is constant, I can move that out, and I just have to do integral dt, which is t minus 0, where t is 5, equals so 2500 for the mass. Velocity is 40 kilometers per hour, so the same conversion. I could have just got rid of the mass or a factor. So 100 times 1000 divided by 3600 plus mu k, which is a constant, it's an unknown, times 9.81 T is 5 minus 0 equals 40 times 1000. Okay, so single unknown, and solve for it. Mu k equals 0.34.
Whenever you calculated it, you get your velocity is like in the positive direction. Did you get a negative or a positive?
Oh yeah, good catch. This is clearly not right. Hold on.
What you would say that
Yeah.
backlash is a positive direction.
Hold on. Yeah, absolutely right. So I did a mistake here, and it's glad you brought it up. Okay, so our convention is, well, we can either stick to our usual convention is right side is positive, right? If you do that, then this velocity is negative and this velocity is negative. And then friction force, my bad. Velocity is negative and force is positive, right? Yeah, force is positive. And so I forgot the negative sign. In fact, if you don't have the negative sign, you'll get the wrong answer. Yeah, I mean, yeah, so that's converting kilometers per hour to meters per second.
But yeah, negative for velocity.
Either way, you can put negative for friction or you can put negative for velocity. Just stick to some convention which you like and stick to it. Okay, any questions on this? Okay, let's move on to the next one. The assembly consists of two blocks A and B, which have a mass of 20 and 30 kilograms. So 20 and 30. Determine the speed of each block when B descends 1.5 meters. The blocks are released from rest. So the speed of A, the speed of B when B descends, so let's call that delta Y, P equals 1.5. Okay, so here's what I want you to do. Talk to your neighboring person, and try to identify which principle you'll apply from the formula. Okay? Pause for 30 seconds, talk with the neighbor, and then I'll go ahead and solve it. So question is, that's the problem. We got to figure out which principle to apply. Go through the sheet and identify which principle you apply. It's either 2A, 2B, 3A, 3B, or 4. There's just 5 options. If you came late, you want to write on the stage. This one right there. Touch it. Okay, done. So, so how many think it's 2A? Okay, 2B. Okay, it's clearly not 3 because there's no time involved. What about 4? Could you apply 4? Okay, so 2A is the right answer, but remember one thing: if you are stuck with that, and you know it's a dynamics problem, you'll always be able to solve it using 4 equations of motion. Equations of motion always work, no matter what. So if you're confused, use 4A. Sorry, use 4. Okay, so we'll solve it using 2A, but you should try to do it using 4, that is equations of motion, and try to check your answer. So 2A is conservation of energy, and that's because the only forces in this case are gravity, and so energy is conserved. So principle of conservation of energy. Okay, and because I would need to let me just put down the expression and then try to derive whatever I need to solve the problem. So T1 plus V1 equals T2 plus V2. Okay, so initially the blocks are at rest. So initial kinetic energy is 0. To find the potential energy, I need to have a datum for gravity. So let's see. Okay, let's choose this to be the datum. And then I'm going to write variables to describe the motion of this point. Let's call that y a, and then I call it y, and that's the motion of a because this link is rigid and the displacement of that point here is the same as the displacement of a. And for b, let me put this to be the distance. Okay, so now using the datum I can write the potential energy is m a g y a. Okay, and what's the sign on that? Is it positive? It's negative, right? When you're below the datum, negative potential; above the datum, positive. And similarly, it's going to be m b g y b. Equals, there is, when the system moves freely, it's going to have, both blocks are going to have some speed. So f mva square plus half m mava square mb vb square. And then I need to write the potential. So mg, so mag, so what's going to happen is b is going to descend down by 1.5 and a is going to descend up. Is that right? Yeah, it's going to go up. Is that right? Yeah. So, and we do not quite know how much a is going to descend up. So let's put that to be negative delta YA. Then we got to find that. So the new potential of A is going to be, well, it's MAG times the displacement. So that's going to be YA minus delta YA, right? Because the distance has decreased by delta YA. And then for B, it's going to be MBG YB plus 1.5. This is delta YB. I can simplify this a little bit, and you can notice that there's MA. By the way, I forgot to put the sign. The sign is incorrect. It should be negative, right? Because both of them are below the datum. So I can do a little bit simplification here. MAGYA on the left side will cancel with MAGYA on the right side. Similarly, MBGYB will cancel with MBGYB on the right side, and I'll be left with 0 equals half MAVA square plus half MBVB square minus is plus MAG delta YA minus MBG times 1.5. Okay, VA is an unknown, VB is an unknown, delta YA is an unknown, and so I have a single equation with 3 unknowns. I would not be able to solve that equation unless I get extra equations. So here's where you're going to realize that now it's a kinematics problem. You're going to figure out a relation between them, and this is where what you learned in the previous chapter 12, your previous exam, comes handy. So this involves finding the length of the cable and then differentiating it to get an expression. So let's find an expression for the length of the cable. So the length is, well, YB for the rightmost length, and then there is YA for the leftmost length, and then there is this part and this part, but that is connected. Well, let me write this as D. That's the length of this link. So this length, the length of the cable I've shown here, is going to be, you can take this much, it's going to be twice YA minus twice D, right? So that's YB plus 3YA minus 2D. And so when I differentiate with respect to time, I get L dot equals YB dot plus 3YA dot equal to 0. This can be written in 2 ways. One is velocity of A plus 3 times velocity of B is equal to 0, because the rate of change, sorry, this should be YB, VB plus 3VA, because the rate of change of Y with respect to time is the velocity, and same for A. And I can also write this as delta YB plus 3 delta YA equals 0. And that's because Y dot B is delta Y divided by delta T, delta Y divided by T, and that delta T just cancels off. So the first relation gives me the rate of change of velocities, how they're related. The second one gives how displacements are related. So from the second one, I can write delta YA equals minus delta YB times 3 divided by 3 equals, delta YB is 1.5, so minus 0.5. So that delta y is actually telling me that if b goes down 1.5, y would go up by 0.5 meters. So one issue is that I already assumed that, if you look there, I already assumed that delta y is negative delta y. So if I put negative 0.5, actually that won't be, that will not be right. I'll have to take the magnitude of 0.5 because I took minus delta y. I should have taken plus delta y, then I would have just kept the sign. So this 0.5, only the 0.5 needs to go in this equation. And for VA, it's, so let me write this equation down again, equation 3. Zero equals half m, let's keep VA as it is, and then sub in for VB, half MB VB, which is, I already found that VB is minus 3VA from equation 1, so minus 3VA square plus MAG delta y, as I said, should be 0.5 and not negative 0.5 because I already started off assuming that y is upward. If I had not assumed it that way, I had taken it, if I had not made any assumptions earlier on, then I should have put minus 0.5. Minus MBG 1.5. And so in this equation now, I have only a single unknown, VA.
So 0.5 is positive?
It's positive because, okay, if maybe this is confusing, but here's the, let me backtrack and this will remove the confusion. When you start off, you do not know if A will move up and down. Just let's stick with that. In which case delta y is down, right? Delta y is positive downwards. So this is not assuming anything to do with delta y. We're going to assume it's to be down because our convention is downwards is positive. Stay with that convention. So this will be positive. So this will be negative. Okay, and then at the end, it's right to put negative 0.5 now. And this will actually be better than, so the way we do problems, and I sort of violated that, is always start assuming positive for whatever variables are, and then do the math, and the math will tell you if your direction was right or wrong. So in the similar vein, I start off with delta y, a positive downwards. I'm not assuming anything. I put that in as it is. I get a negative sign, and then I figured out it's negative, so I put the value with the right sign, and now the math should work out. So this is probably the cleanest way of doing it. Okay, if you solve for PA, you get 1.54, and VB get 4.62. Yeah.
Oh, what are the initial potential energies for the top group? Why are they negative?
Well, it all depends on the datum. If this is the datum,
Yeah.
and we are trying to find the potential of, let's say, A, which is the same as finding the potential of this point. So the potential is always above the datum is positive, below the datum is negative.
Okay.
Below the datum, so it's minus mgy. That comes
Yeah,
from
so
being,
below it, and
yeah.
then B would go up, so it would gain potential energy, so that would be positive, right?
B would lose
go down.
potential.
Yeah, B would go down.
We'd lose potential energy.
Yeah, so that would be mine. So then A would go up, so it would gain potential energy.
Yeah, but what I'm trying to do is I'm not going to assume it going up or down. I'm going to assume that A and B both move down. The reason being,
Okay.
I do not know which is going up and down. That's how I begin with. And that's why I have YA plus delta Y and YB plus 1.5. And then the math tells me, well, that's not true.
Yeah.
It's actually negative.
Okay.
And then I put that in. So that's the cleanest way of doing it. No confusion. It's so very algorithmic.
Okay.
Okay, any questions? Okay, so as I said, you could totally do this problem with F equals ma. What you have to do is draw free body diagrams for the individual masses, find the acceleration of A, acceleration of B, and then once you have the acceleration, you can integrate the acceleration to find the velocity. So that's another way. If you think this is confusing, use F equals ma. F equals ma always works. By the way, any questions on that problem? At the instant theta equals 60 degrees, the boy's center of mass g is momentarily at rest. So when theta is 60, velocity is 0. Determine his speed and tension in each of the two supporting cords of the swing when theta is 90 degrees. Okay, which means that he would be in this position. The boy has a weight of 60 pounds. Neglect the size and mass of the seat and cords. Okay, so the question is, find the speed when theta is 90 degrees and find the tension when theta is 90 degrees. Okay, so let's look at the first part. Can you talk with the student near you and see what principle you'll apply to solve for the first part? I'll give the answer in like 30 seconds. So it could be 2A, 2B, 3A, 3B, or 4. Okay, talk to your neighbor, see what principle you apply for part 1. How to find velocity when theta is 90 degrees.
Yeah.
So what do you think? How many think it's 4? Okay, and how many think it's either 2A or 2B? Okay, so you could do it with either 2A, 2B will work well. It's not. In this case, it's 2A, right? Because there are only conservative forces. You could also do it with 4. So the solutions. This is actually a problem from chapter 30. Okay, but what I'll do is I'll show you how to solve it using 2A, which is slightly different approach, but you'll see that you get the same answer. So as I said again, 2A will make your life easy then, and not that 4 is hard, just that you'll have to integrate an integral. So I'm going to use 2A because there are only conservative forces. So I invoke the principle of conservation of energy, okay, which states that T1 plus V1 equals T2 plus V2. Okay, I could choose the datum here. That's one option. Why don't I choose the datum here? Just to give some variety, but you'll see that the answer does not depend on where you choose the datum. You should get the same answer. Let's choose this to be the datum. That is when G is at 60 degrees. Okay, so T1 is 0 because the kinetic energy is 0. Since we chose the datum to be at G, initially the potential is 0. T2 is half mv2 square, that's the velocity here, we call it v2, plus the potential at 2. So that's going to be the distance from the datum to the point, right? This distance. And that distance is 10 times, so that's 10. And then this height is going to be 10 sine 60, right? So this length is going to be 10 minus 10 sine 60 degrees. So mg times the distance from the datum, which is 10 minus 10 sine 60. And is the sign right on this? Is it positive? Is the potential positive or negative? Negative, so this is not right. It should be negative. So I can cancel m. V2 square equals 2g 10 minus 10 sine 60 degrees. 32.2. So V2 equals 9.289 feet per second. Okay, the way the book does it is using equations of motion. Okay, so second part. Okay, when you're asked to find the tension or any force, you're stuck with using equations of motion. There's no other way to get it unless it was a very special problem like the first problem where we got the friction coefficient from using principle of impulse momentum. So we got to draw a free body diagram of the system at theta equals 90 degrees. I recommend that you draw a free body diagram at a generic angle theta and then put theta equals 90 because sometimes you miss out on forces if you don't do that. So let's draw a free body diagram at a generic angle theta. Okay, so if you want to use equations of motion, then you got to figure out what coordinate system to use. Since the swing moves in a circular fashion, both conventions, nt coordinates as well as r theta would give you are good choices. Okay, you can do either one. I normally recommend nt, but r theta is fine too. So for nt, ut is the direction along the tangent and un is the normal direction. So equations of motion. So I only need the equation in the n direction because that will help me solve for t. So t, which is in the minus un direction, now let me write Fn equals mass times An. So Fn is minus t because, plus t because it's in the un direction. And then I need to resolve mg in this direction. So it's 90 minus theta is the angle made by the vertical with the tension. So mg cosine 90 minus theta, and since it's in the direction negative un direction, I need to put a negative sign, equals m v dot, no, v square divided by rho, which is the length. So t equals mg cosine 90 minus theta is sine of theta plus mv square divided by rho. So T is mg, which is 60 sine of 90 degrees, because theta is 90, plus m is 60 divided by 32.2. Velocity is 9.289 square, and rho is the length of the cable, which is 10. Yeah, so that comes out to be 38 lb.
Now, is that for one tension, or is that for both?
It's just one tension. It's along even direction. There's no.
I was thinking of like, is it set for each chord?
Oh, so
Two,